All right, we're going to take a look for the first time here at solving simple absolute value equations and inequalities. Kind of struggled with where to put this because we are going to see absolute value equations and inequalities applied to trigonometric functions and equations, quadratics, other polynomials. We're going to look at functions like this and transformations. So they really do keep coming back. We're just going to look at some short ones here, some simple ones, and see some set notation, interval notation, solve simple linear equations in this way, and make sure you have the basics for going forward with rather simple equations for now. Remember that the absolute value or modulus function is denoted by these vertical lines, not to be confused with ones. And we're going to solve them kind of like we do anything else, and then consider what that means when that's the only thing remaining on that particular side. So if you remember, the absolute value just is the magnitude or the distance it is from zero. So I'm going to consider this in PEMDAS my group, my parentheses, even though they look kind of different here, that top thing. And I'm going to undo the minus 17 first, and then divided by negative 3. So 8 minus 17 is going to be negative 9. And then I have, I guess I can write this here, absolute value. And as someone who grew up writing ones as just a straight line, I make them especially big so it's clear that they're not going to turn into ones. You don't have to if your ones are kind of the German one or whatever else. And then I get, now that I've kind of gotten better at distinguishing my ones, it doesn't really matter too much. So positive 3. If you did get a negative answer on this side, there's no solution, because remember, as the distance away from 0, there's no way that distance is going to be negative. It says take whatever's in there, make it positive, so it can't be negative. That's the whole definition. We do have a positive, so it's fine to go on, but some of these can't be solved. And what this means, because it takes whatever is in here and it makes it positive, it could mean that on the one hand, it already is positive. 2x minus 5 already is 3. Or it could mean, well, 2x minus 5 could also be negative 3. Okay, and in that check you did at the beginning, it looked like many of you had seen that and understood that. And then I just solved both of these as if there were no absolute value, because there really isn't anymore. So adding 5 to both sides. One common mistake that people do here, once I divide by 2, is going to give me 4 as one solution. Just be careful as you add 5 to this side, you're not going to get negative 8. Super easy to make that mistake. As you add 5 to this side, you actually get positive 2. So x could also equal 1. Okay. So there are 2 solutions to this because of the nature of the absolute value in this case. Here's one that's slightly trickier because again, I already have the absolute value on one side, so it means whatever's in here could be positive of this. That's one way to solve it. So 6x plus 2 equals 3x plus 7. Or it could be that it's negative, but the whole thing is then negative. Be careful that you're not just making the negative 3x, for example, negative. And then we'd solve both of these. So minus 3x from both sides, minus 2 from both sides. I'm not going to be pedantic in solving these linear equations, because hopefully, if you've gotten this far, you know that. And subtracting 2. So 3x and then take away 2. X could be 5/3. Okay, or you have this on the other hand, what I'm going to multiply out here is going to give me the negative 7. I'm going to add 7 to both sides. Doesn't matter which way you do it, of course, and take away 6x. So 9x. So we could also have that negative 1 equals x here. You should always check these kinds of things, especially as you get into extraneous solutions, and that will become more of an issue as we look at slightly more complicated ones here. I do want to make sure that it's true even given this. So 5/3 of 6 is going to be 10 plus 2 is 12. 5/3 is this, is going to be 5 plus 7 is 12. The absolute value of 12 was 12, so that one's good. If I put in negative 1, this is going to give me negative 4, right? But the absolute value of negative 4 is 4, and this will give me negative 3 plus 7 is also 4, so 4 does equal 4. So both of these are solutions. When you have absolute values on both sides, what you can kind of think of as you're doing the same thing. But of course, if they're both positive, well, that's quite simple here. X plus 3 is 2x minus 8. Or you could say, well, they're both negative, but if they're both negative, well, then I can divide away by the negative and I get the same thing. I could say, well, I'm going to make the one side negative, so I get x plus 3 equals negative 2. That's going to be a 2, x minus 8. Or I could make the other side negative, but that would give me, in the end, the same because I'm really just swapping the negative side. So we still do have this negative or positive situation with two different options, even though theoretically it's because 4 things could be reduced down to the 2. If you have more going on either side, like absolute value plus 1, okay, then it's going to be quite a bit more complicated, but we don't need to look at that. And then you just solve each of these just like you did on the other hand. So I will take away x from this side and add 8 at the same time. So 11 is equal to 3. Excuse me, I wanted to take away. So 11 is equal to x, nice and simple. And then if I multiply out my negatives, okay, and I'm going to then take away 3 and add 2x. I'm going to get 3x on this side, taking away 3 equals 5/3. Okay, again, you could check this. I get that 14 equals 22 minus 8 is also 14. Both were positive. Those are true. And 5/3 plus 3 is going to be, I like to consider this as a decimal, so 1.67. Let's call it that. We'll see it anyway. So 4.67 and 2 times these 10/3 is going to be, 2. That works out when we make that positive as well. Good. If you were to see the graphs, and we will see the graphs of these, you'll see that they'll also cross just twice. They'll intersect each other. So now looking at the inequalities in absolute value. On this side, I've just made, well, I've copied and pasted a table of what this could look like in different ways. I'm sure you've seen many of these things where you either have brackets, meaning that it's inclusive. So like if x is greater than or equal to some number, we'd have these square brackets. And if we were to put it on a line graph or even on the coordinate plane, we would put a filled in circle. If you have something where it's not included, so explicitly less than or greater than, then we use regular parentheses and leave the circle open. And you can use any combination of those. Going to infinity, of course, we wouldn't then write infinity with this inequality notation. And we can't ever actually equal infinity, so we use the parenthesis and just write the arrow that it goes on forever and ever. And you can see that then in both directions there. As you have absolute value inequalities, you do, sometimes it's just easier to find where they're equal and then check a few values in between. But if the absolute value of some number is less than a value, like if I were to say the absolute value of x is less than 4, that could mean that x is going to be between -4 and +4. So if you were to say like, well, -3, is the absolute value of -3 less than 4? Yeah, because 3 is less than 4. -5 is less than 4, of course, but the absolute value of -5 is not less than 4. So that's why we get it in between. And if I were to show what that looks like then on a line graph, I would want to use an open circle, as you see over here, and then somehow indicate that you are including solutions between those. Of course, if this had a line underneath in either way, you would have to fill in those circles, but for this, it's explicitly less than, greater than, and the other way around. So if you have that this absolute value is greater than some value, that actually implies that you're going to need to separate it into an or argument. Of course, it can't be and, it can't be bigger than 10 or less than 10. If I said, for example, the absolute value of x is going to be greater than 6, so 7 is greater than 6. The absolute value of 7 is also greater than 6, and I would need an arrow to indicate that. But also, -7 is not greater than 6, but the absolute value of -7 is, because 7 is greater than 6. And that's true for anything explicitly less than -6. So we do get this kind of two-piece thing here. And those are all the different notations. If you haven't seen them and you're not comfortable, write them down. You will see them over and over again, though, so you don't have to worry too much about it. One thing you need to remember about solving inequalities, and really one of the main things that makes them different than solving equations, is when you multiply or divide by a negative number, remember multiplying and dividing are actually the same thing, you need to flip the sign. So if I subtract 15 first, -1/2 of the absolute value of 3x minus 5, and then I take away this. It's not a problem if I'm subtracting or adding negative, positive numbers. That's fine. Taking away 15 from that is going to give me negative 8. And then when I divide, though, by negative half, I am going to want to flip it to this, right? And negative 8 divided by negative half is positive 16. It's not negative 4, positive 4, anything like that. You can kind of consider this as an equal sign going, okay, and I will for a moment, and then we'll just have to come back to this. I think it is easier to do that. You do have a few different options of how you want to do it, but we could say, okay, that stuff here is going to be less than 16 if it's positive, okay, or, and you can solve this as if it's an equal sign too, and then check it like I just said, okay, and I'm going to come back to it here. You can also see here what I'm going to do. If you compare this, we have this absolute value of something is less than or equal to it. So here, then I get it between these two things. So it could be that this is greater than the negative value. Okay. And if you solve each of these, subtracting 5, dividing by 3, I'm not dividing or multiplying by any negative number, so I don't need to flip the signs, adding 21. Or if I add 5 to this, I get then negative 11. Negative 11 thirds. Okay, and if you were to put this on a number line, or you could even say, okay, so negative 11 thirds, x is going to be between these values. You don't need to write it separate in this particular case because it is possible to be between those. And